I just want to make an observation here, which is pertinent to what I'm going to do. Most contemporary philosophical naturalism, insofar as I'm aware, is almost completely oblivious to the fact that a reasonable naturalism has to underwrite the answers that mathematicians have developed to these questions. Applied mathematicians can give us quite good reasons why those series computations break down when they succeed. Now, there's actually many continuing mysteries. They've given us a lot of good answers, and there are a lot of mysteries remaining. Is the truth. Okay. And I wanted to say, as opposed to Hartree, who's, I know from talking to him, completely ignores these kind of problems, there are lots of prospects in what Michael is doing that, from a neo-Kantian point of view, can supply better answers. Now, I don't want to particularly go Michael's way myself, but this does need to be understood. And in fact, it should be recognized that many of the great mathematicians of the 19th century who developed some of our most basic understanding of reasoning technique were very attracted to Kant's philosophy, precisely because of this reason. Okay, now, what I want to do is, there's more of this in the book. I'll try to hurry past this sort of stuff. What you need to do to understand your computational place is to have you on one side with your computations and the world out there, and you can build a mathematical model of that interaction. Or not interaction, but parallelism or failure of parallelism. Okay, so you want your reasoning patterns R and the worldly behaviors C, to which the pattern's trying to pull out answers, reliable the reasoning pattern trying to get answers. Okay, so I have a picture of Groucho and Harpo from Doug Soup. They're hopefully meant to be a copying relationship. Well, that's actually misleading. Hertz uses that metaphor, but actually, in almost every realistic case, the patterns that the calculations go through and the patterns that the physical system goes through are very different in character. Okay, often so-called structuralists, people who want to be structuralists about mathematics, will blithely talk about isomorphisms or partial isomorphisms between mathematical structure and the world. They're usually being very sloppy about what they mean by mathematical structure. If we mean computational pattern, which is what they half the time think they mean, it's just really wrong. In any study of any reliable physical technique will show you that. I'm actually going to talk about the one that most comes closest to exemplifying that isomorphic picture, or most of them don't know. Now, I'll try to get through this quickly. The basic framework that you've got to do, since we really don't, and the only reason to calculate is because we don't know what the world's going to do. Okay, so to make these sort of studies, what you have to do is look at the possible behavior of the world in huge classes that are wide enough to model any feasible manner in which the real world might make the data you have at hand true. Okay. Now, it's easier to explain this for example. Okay, we're going to look at differential equations. They exemplify the problem nicely. So we could have a very simple model of a bead sliding along a wire where its velocity is dependent upon its position. Okay. Now we don't know, if you start that off with a particular velocity, you don't know in what pattern it's going to just form. And if the function of position that gives you the velocity were complicated, you'd be foolish to think that you'd know how it was actually going to wiggle. So it could do anything within some class of continuous trajectories. Okay, because our formula only fixes how the bead behaves at an infinitesimal moment. It doesn't tell you how the bead moves over any observable time length or scale. And that's what you want to do. That's what inference is in this context. At least one question you want to answer is, how does it move over some time? Okay, now, this inferential rule is sort of the prototype of a lot of better computer programs for plotting trajectories is Euler's method. And as I said, I talk about this in my book, this comes closest to implementing that computation in structure pattern matches the pattern in nature. It's still not a perfect match here, and that's what I want to emphasize. Okay, Euler's reasoning rule is pretty simple, very simple. You got your point P, if you have you can calculate what the velocity is supposed to be there. Okay, then take a little time interval, real short, and assume that the bead holds that velocity over that time interval, taking it to point Q. Okay, and then keep going. That's Euler's method. Okay. Now is that, and so we got the real trajectory of the bead, which will be curving. This will be a sort of straight line plot that, depending on how short we make this time scale, should come kind of close to C. If it comes close, that's good. We've got a pretty reliable picture. We've extracted reliable information from our equation. Okay. But, I hate PDS. Okay, we're missing a delta T there, that's all. Okay. No, Euler's method kind of flies by autopilot over the interval. It says, give me the velocity at P, I'm just going to fly blindly with that velocity to get to Q. Okay, but you know, just like with airplanes, horrible things can happen in between. Like, yeah, you can have some little kick in the velocity field on the wire that would kick it off in some completely different direction. Okay. And this isn't an idle worry, right? Many of a computer, a naive plotting procedure on a computer will often just give horrible results, basically for this reason. Okay. There is still some worry that the basic computer plots that people use in chaos theories to get a sense of how differential equations could be, to a large extent, artifacts of the failures of numerical methods, which is how they go. There's been a lot of checking on this, but to show rigorously that the Lorentz attractor is correct is very hard. And these difficulties trace to the fact that finite humans can only inspect how C behaves at staggered delta T intervals. And that leaves a lot of room for the process we're actually studying to do something different than what we get through our inference. So at best, we can hope that our Euler path will become close to the true path if you make your time steps close enough. But that doesn't always happen, and you have to place additional provisos on the equation before you can get that guarantee. Okay. Now, showing that all of this happens for a specific class of equations called a correctness proof by the mathematicians is Euler's method. They've been studied since Cauchy and this particular method since Picard in the 19th century. Now, getting these correctness results is usually really hard. And the results we have usually fall way short of the assurances that practicing physicists would like to see, say in the example of chaos theory. So a substantial amount of scientific reasoning advances in the hazy twilight where you're using inference rules that are neither known to be sound or unsound. And in fact, the very calculations that Cauchy originally worried about in celestial mechanics have still not been completely answered, whether they're sound or not, in exactly the region he was worried about. Despite 200 years of the work by the greatest mathematicians in the intervening years.